I think we can go live now. Ready?
Uh,
You can double check.
yes.
See it?
Yeah, we're ready.
Hello and welcome to today's brand new episode of Corecast. I'm your host, Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, I do ask us questions during the episode and we'll get to them. So without further ado, let's get to it. So Tim, last episode we talked about the potential of a fifth force. We had talked about like maybe the force is heavy or light. And for those who don't who's have a question mark on that, check out our last episode where we described that a little more in depth. But I guess like we never talk much about like candidates, like explicitly candidates for like what a fifth force could be. Since we talked about how you would be able to tell if there was a fifth force. But so Tim, I guess now what would be a reasonable candidate for a fifth force if you were to put money on it?
Yeah, so I think in particle physics, physicists always tend to be economical. And the idea is that if you add a new fifth force, first of all, it should do something for you. We shouldn't just have a fifth force for nothing, right? It needs to do something. And second of all, that fifth force needs to be somewhat reasonable. It shouldn't be like too crazy, right? We shouldn't just have like a new force shooting out of our fingers because we don't see that, right? So that's not possible. And it just happens that there is a very tentative candidate, and it lies in the intersection of some of the puzzles that we have. For instance, last episode we talked about, or in many episodes, we talk about the existence of dark matter. We don't know what dark matter is. We just know that it exists, and it's very natural that dark matter could harbor a force that we have not seen yet. So these would be dark forces. Or that's a reasonable name. So it's very reasonable to think that dark matter might be able to feel this new dark forces. And then we also look at the forces that we have. You know, nature is great at creating different variety of forces. So a very natural place to ask is it possible to have some new forces that are similar to the ones that we have right now, but somehow only dark matter feels it? And it turns out there is a very natural candidate, and this is what's called a dark light, or dark photon, dark electromagnetism, if you like. And it's really kind of like a twin of the ordinary electromagnetism, but dark to the extent that only dark matter might feel it, or something like the dark matter will feel it, but we don't. So this goes under the umbrella of, I guess, dark light, but you know.
Yeah, no, that's an interesting name. Before we go into dark light, I wanna just take a step back and ask a few questions about a few terms that you mentioned, just to clarify for our audience. So when you say like dark forces, the use of the word dark, why the use of the word dark, and why is it that like dark matter feels forces that we may not feel, just to kind of give the audience a landscape of that.
Right. The reason it's dark is just a matter of observation. Because imagine if we had a fifth force and we feel it, then we would have known about it already. Like if literally I can push, I don't know, the monitor here, or push Yusa here with the fifth force, you would have felt it. It would have been no secret anymore. It wouldn't be crazy. Like I can just, like, I don't know, Star Wars just like feel the force. Like we would have felt the force. The truth is we don't feel the force. So whatever new forces there should be has to be hidden in some ways. So from that perspective, it has to be dark. But it's more than that, because we want to link it to dark matter. I guess the name dark matter is stuck because, you know, we don't see it. It's not visible. It doesn't emit light. So if dark matter feel these forces, these extra forces will also be dark in a similar vein. It must have very little interaction with ordinary stuff. It must be mostly invisible to us. So for these two reasons combined together, I think it's reasonable to call them dark forces. Although it does invoke a little bit of sci-fi-esque feeling. Like there's nothing evil or like creepy about these forces. Let me just just make sure that we're on the same page. It's just I don't know. Physicists are playful with words, but I guess it's not really that playful of a word. It's just dark forces. We haven't seen them yet. So
Yeah. So what one question I have is like dark matter when we discussed it a few episodes back, or maybe in the most recent episode, interacts with gravity. We also interact with gravity. So like is it that we can't really interact with these? I presumably if there was a force like a dark force, it would also interact with gravity as well. And so I'm wondering like what is the difficulty with that? Like why can't we do sort of
yeah,
gravitate?
yeah. So dark force could definitely interact with gravity, but as you mentioned, you know, in order for us to see gravity's effect on dark matter, you have to look at very large scale, like
Mhm.
size something that's of the size of galaxies, right?
Mhm.
And so yeah, gravity could be involved, but even then, we're not going to be able to see the effects of these dark forces, and their association with gravity until you look at cosmology. And definitely, when physicists were considering possibility of dark forces, yeah, there could be cosmological implications. But the more interesting realm, I would say, is dark forces. We could actually feel dark forces. Maybe it's weak, but we could feel it if the experiments are sensitive enough, right? Or if we try hard enough, we might really be able to feel these minute effects of dark forces.
I see. I see. Yeah, that would be interesting. So you mentioned a potential candidate of one of these dark forces, which has a very oxymoronic name, dark light. I'm curious, like to me that seems like two complete opposites. Like light,
Mhm.
where there is no light, there's dark, and where there's no darkness, there's light. Like, how can you have like dark light? Like what does that even mean?
Yeah, it does sound a little oxymoronic, but actually it's not that crazy if you think about it. Um,
Okay.
so first of all, you can ask the question, why electromagnetism? Well, electromagnetism turns out to be one of the simplest type of forces. It's very simple. There's only one particle of light, basically, the photon, right? And we see it everywhere. The sun is shining light on us. You can wear your sunglasses. You can see different polarization, and there's all these properties. Like you can measure the electromagnetic field. You can use a magnet. You can see lightning. All these are electromagnetic phenomena. So this is very familiar to us. And there are the other forces, like the strong forces and the weak force. Those are a little more subtle, more nuanced, more complicated. And mathematically, they are more complicated too. So something like the electromagnetism is very reasonable. It just means that there's an additional force field in the universe, right? But then you ask the question, well, how come we feel electromagnetism, right? The fact that it's a light, how come we see light? And if you dig a little deeper, ultimately it's just the fact that we're made up mostly of electrons and protons, right? And these are just two types of particles, and that's it, really. The reason we see light is because of them. Like imagine if somehow we were made up of neutrinos. These are particles that the sun create, and there are, I don't know, hundreds of them passing through us. I don't know exactly the number. Well, neutrinos don't see light. They don't have charge. They just pass through us. Or neutrons don't really see light because they're neutral, right?
Mhm.
So 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 when we talk about the word dark photon, dark light, is only dark because we are the wrong species. We don't have the right oomph or the right charges to be seeing them. So maybe there could be speculatively there could be dark beings, although I don't believe it, but dark matter, maybe they can see dark light. Maybe they don't see visible light, right? Because we can't see dark matter. Dark matter doesn't emit light, so dark matter probably doesn't see visible light. Or if hypothetically, if they're dark beings, creatures made up of these dark matter stuff, well, they probably won't see our ordinary light. They will call our light dark, right? So even though it sounds kind of contradictory, but it's not. Really, it's just very natural to have maybe extra forces like electromagnetism, but somehow we're just made up of the wrong stuff. And really, remember that the stuff that we are made up of, baryonic matter, it's only 5% of the energy budget of the universe. It's not even the majority. I mean, that's not crazy to believe that. Look, maybe dark forces is really way more prevalent than we thought. We're just kind of the wrong stuff to see it. So it's not insane.
Uh, that is interesting. I wonder like are there even simpler particles that could be a dark force like without going too much in the technical details like a dark Higgs boson or something like that
Yeah,
instead.
yeah. I would say this would be the like the dark light would be the simplest example. I think the Higgs boson you can argue maybe you wouldn't necessarily call it a force. I mean, there's a mathematical lingo. There's no symmetry associated with it. It doesn't have the right particle property. There aren't
I
like
see.
charges on the Higgs boson, right? So the dark light, as
Hmm.
complicated as it sounds, is the simplest example of a fifth force. I think I can defend that.
I see. And so just to kind of clarify this, because like when I first hear dark light, like based on English nomenclature, common vernacular, it sounds like very contradictory. But what you're saying is it's like it's a dark force that is similar in mathematical structure and other properties to how we like interact with light, except this would apply to dark matter in that sense.
Yeah,
Is that
exactly. It's only dark to us. It's not dark universally.
Hmm. Gotcha, gotcha. So I guess like what was even the motivation of like coming up with this? Like I guess like why yeah, like I mean presumably somebody came up with the name Dark Light. Is there like any history of this that you could give or any like context of how this arose?
Yeah, I don't think the name really stuck. I mean, in particle physics, they refer to the particle more so than dark light. So we used to talk about dark photon, and photon is a particle of light that we normally see. I don't think the name came to be. I think I was reviewing some papers. I think in 1980s there were some paper that talk about hypothetically there could be kind of like a duplicate twin of the electromagnetism, but nobody came up with the term dark photons. I think using this kind of theoretical model to talk about dark matter came to be when at some point there was some satellite experiments. I forgot which one. They observed some excess cosmic rays. They were seeing a lot of positrons for some reason, and in our universe, there are a bunch of electrons, protons spinning around galaxies and hitting the Earth all the time, or around the Earth. So cosmic rays are no surprise. But positrons are a little tough to make. These are anti-matter. Just keep that in mind. Now, if you fling protons around, yeah, you can generate other protons and stuff. But anti-electron, like positrons, it's a little tough. So people were trying to explain that phenomenon to say that, hey, look, maybe dark matter has these new dark forces, and they annihilate. So when one dark matter meet another, they could annihilate each other. Possibility. It's just a speculation. And when that happens, they can produce dark light, and these dark light could be a little different from ordinary light in that they could decay, or ordinary light doesn't decay. But dark light, there's no because it's dark. It could have slightly different properties than ordinary light. So they might be able to decay into electron and positrons, right? So that's when the whole thing I think really pick up steam. But since then, I mean that those models have been ruled out now. Now we don't think those positrons were coming from dark light. But now there's a whole theoretical paradigm of studying what are the possibilities of these dark forces. And they're, you know, I think part of it is just curiosity. It's like, what if? What if this is true? Because we haven't seen dark matter. What if this is true? And it turns out the physics is fascinating. There's so many variety of phenomenon dark light can do for you. And some of them are rather unexpected actually. It's not what you expect.
Huh. So I guess like what are some distinctions besides like besides like dark photons interacting with dark matter? Is there like a difference or is it exactly the same except they just interact with like dark matter instead?
I think there is a difference. So the key difference is that the the light that we have is what we call massless. And in quantum physics, massless is, when something sort of mass and length is somewhat related. So because particles are waves, for something that's massless, it can have an infinite size. The size of a particle is roughly its wavelength, right? So if you look at a particle of light, because it's kind of like a wave. So the lower the energy the particle of light, the larger this particle of light can be, right? So it tells you that the particle of light can have all sorts of energy ranges, and its influence can propagate an infinite distance. That's why you can see very distant galaxy and their light from Earth. But dark light could have slightly different property. It could have a non-zero mass. It doesn't have to be massless anymore, right? And that means that its length scale of influence might be confined. Maybe dark light couldn't move very far. It could decay, or you might not be able to feel dark light after a certain distance. So those give like a distinctive flavor that the dark light physics it's a little bit different. Yeah. So and that leads to interesting phenomenon.
Gotcha. There's an audience question that I want to ask. Says, would we have four fundamental forces in the dark universe also?
Well, I mean, we already have four fundamental forces, but we know from experiment that the dark matter mostly do not feel those four fundamental. Dark matter feels gravity, okay, but dark matter does not feel three of the four fundamental forces, right? So if we add dark light, yeah, there will be five fundamental forces, and then, gravity is universal. Three of them we will feel, and one of them, mostly dark matter, will feel. And there could be more actually. And this is just one of the first possibility to study.
Okay. Another audience question is, would dark light have a speed limit like regular light?
Yep, absolutely. They are confined by regular physics just as much as the other forces and the other particles. So yeah, even though dark light sounds mysterious, we actually could know quite a lot about it once we make some assumptions.
Yeah, that does make sense. I guess, Tim, if I like came to you and said like, "Hey Tim, I've discovered dark light," what would you need to see to be convinced, like without a shadow of a doubt, that like this exists? Like, wow, this is here.
Yeah, well, first of all, if you have dark light, it's probably super difficult to contain, I imagine, because because we know it's very dark. I mean, chances that once you hold it in your hands, it probably has escaped already. But okay, if you have a vat of dark light, I would just put it inside a detector and just wait for it to decay, which is probably pretty quickly, and to see what the decay products are, right? So there are two possibilities. Dark light may or might not decay. Okay, if dark light is exactly like normal light, it could move exactly at the speed of light. It can be massless, and it can permeate the universe, just like how in the night sky you see stars shining. There could be dark matter shining in dark light, but we couldn't see it because it's dark, right? But if that were to happen, you actually could not have a lot of dark light because we know, using Einstein's equation, how much stuff is in the universe. It turns out that in this scenario, you can only have a little bit of dark light, not too much. Otherwise, the universe will be it's a little technical because dark light will kind of wash out structure. It's kind of smooth. It will smooth out the ups and downs of the densities of the universe. So that could not happen. It will kind of smooth out galaxies, right? So that can't happen. But that's possible. The universe could be based in dark light that we just cannot see if dark light is stable. Yeah. But if dark light is not stable, then of course many of them could decay and probably would have decayed already. And if you have a vat of them, they might just decay into things like positron electrons or some other particles, pions or whatever. And if I stuff it in a detector, just wait for the decay, which is probably really relatively quickly, and just wait for my Nobel Prize. Clearly, right?
I wait next year, Tim. Nobel Prize for dark light. Yeah. Okay. Actually, there's an audience question regarding a clarification to what you had mentioned, saying but you said they can have mass. How would that reconcile with special relativity regarding like dark light having a speed limit?
Yeah, yeah. I would say the reason this confusion arises is because when people say the speed of light, it's not really the speed of light. The speed of light, think of it as a number. It tells you how many meters per second, right? You can think of them as a speed, of course. But I think a better way to think about it, it's a conversion. It's like a currency conversion, like how many US dollars per, I don't know, you know, yen, right? So this is kind of like how much space per time. It's kind of like a barter system. It's really a conversion factor between space and time. And Einstein tells us that space and time are the same thing, and this is really a conversion factor. It just so happens that when a particle has no mass, then the same conversion factor applies to what we call energy and momentum, which is energy is what people are familiar with, and momentum is the energy of motion, right? And when you look at that relation, just so happens that the ratio of them is the speed of light, and then it means that a particle is traveling at the speed of light. But really, the speed of light doesn't have to be a speed, right? So for a dark, for a dark light or dark photon, if it has mass, yeah, it's not going to be traveling at the speed of light. I mean, it's going to be traveling slower than the speed of it, but that's totally okay. Just like every other massive particle. It just, speed of light is not really speed of light, if that makes sense.
Yeah, yeah, I've seen that before. I mean, could you also say it's the speed at which the maximal speed at which information can travel?
Yeah, yeah, yeah. It's just, yeah, it's the cosmic conversion factor, and this information thing is just a consequence of that.
Hmm. Makes sense. Makes sense. Okay, so I've come to you. I've said, hey Tim, I have dark light. I put in this like vat. I give it to you. It decays. I guess like is what if it just never decays? Like it has mass, but it just never decays. Like like an electron kind of a thing.
It's
Situation.
possible. In fact, if dark light has the right masses, which is not zero, let's say, I think there is a range of masses for dark light where it's possible for dark light to be dark matter itself. Dark matter could be dark light. It's possible. I mean, that's why what I'm saying is, one, this concept of dark light was first proposed as kind of like, like a curious thing, like an interesting possibility. Why not, right? But it turns out that depending on the mass of the dark light and how much interaction dark light is, how dark it is, the level of darkness, right? It can fulfill different roles in the universe. And for a particular range of mass, which is way smaller than the electron, I think, probably more like neutrino, which is very, very small, like maybe 1,000th, maybe even smaller than the mass of electron. It could be stable. There's nothing for it to decay into. And it could be dark matter itself. Dark light could be dark matter. How ironic would that be? It's just light but dark, so we can't see it. So, but it's actually interesting. So dark matter might actually be a dark force, and that's a possibility people have studied, and this is it's a legitimate theoretical possibility.
Yeah, that is interesting. I wonder though that like so if it never decays, I guess then how would you be able to tell that it's like dark light? Like what would you need to do to actually like be convinced if it doesn't decay?
Yeah, if it doesn't decay, it gets a little harder, but we can see the remnant effects of this new force, right? Because after all, it's a dark photon is a force mediator, and there should be some remnant of this effect. And there are many, many different possibilities. I'll give you one example for possibility. Like recently, in the past few years, people have studied, if there's dark light, it can affect black holes. Black holes could shine in dark light. It will actually destroy black holes. It's called superradiance, this phenomenon. So you might think that black hole is black, but if a black hole is bask in dark light, it could destroy itself. So that's a possibility. It's a very interesting possibility actually. And the sun could be shining dark light. And these dark light, when going through some detector, it could convert into something else. So we might be able to see something. There's also these really intriguing experiment called light shining through wall. It's almost like science fiction. The idea is kind of like, you can kind of imagine, roughly speaking, it's not precise. They have some particle accelerator, which is tantamount to a massive flashlight, really powerful X-ray flashlight, whatever. You just shine a flashlight and just straight into like a piece of metal or like concrete, and see if on the other side you see the light. And you ask, that sounds crazy. Like you can't shine a light through concrete. Well, but if by chance the normal light get transformed into dark light and comes back, you might actually be able to see ordinary light on, something comes out on the other side, right? So through some of these experiments, I mean, it sounds kind of crazy, but that's what you expect if there's an extra force, right? That's what would happen if there's a fifth force. It's gonna do something kind of unexpected, right? So through these experiments, some of them are very creative. We could establish the existence of this new dark force, basically.
I guess can you explain more about how black holes would like get destroyed by dark light? Like, how does that even happen?
Yeah. So it's a very interesting phenomenon, but I don't want to go too much into the technical details. And you can ask the same thing. Oh, how come black hole doesn't destroy itself under ordinary light? Right? Why not? Well, keep in mind that ordinary light has a variety of energy. So there's no. I think once I explain further, it'll become clear. So when you're given a particle of light, it can have any kinds of energy, right? So there's no particular size for the normal particle of light. But if dark light has a particular mass, that mass is associated with a particular size, a wavelength. Because in quantum physics, energy is inversely proportional to the wavelength of the particle. So a mass is energy, so mass is inversely correlated with the size of a particle. So if dark light happens to have the right kind of like a Goldilocks mass range, that means it's kind of have a Goldilocks size, right? And if that Goldilocks size is roughly the size of a typical black hole, which is roughly the size of the Earth, I think this roughly the size of the Earth, then that means when a black hole, is spinning, it has to do with spinning black hole. It's also going to spin around this dark electromagnetic field, and it will create like a resonance effect. This dark magnetic field, dark electric field will oscillate up and down. And you know what happens when you oscillate a dark field up and down? It's going to shine in this dark light. And it only works if there's a Goldilocks mass for the dark light. And when this oscillation happens, it will just destroy itself. The black hole will destroy itself. So it will destroy itself in a fantastic burst of dark light. It will be like a black light nova, but we wouldn't see it because we can't see dark light. But it will be a fantastic phenomenon. But the fact that we have seen black holes means that those dark light could not exist. So it's a very interesting results.
Well, you're saying that dark light with that specific Goldilocks mass can't really exist because we observe black holes.
Exactly. Yeah, but we don't. Well, we observe black. It has to depend on the spin, and that relates to the mass. So there, this phenomenon could still happen. But the more black holes we've seen, the less likely it is that black hole can be destroyed by dark light, right? But maybe one day when we see, if one day we suddenly see that certain types of black holes just could not exist, then you might say, well, that could be a hint that certain black holes are destroying themselves. But so far there's no evidence. We've seen a lot of black holes, and that means that black holes are not destroying themselves, and yada yada yada. And similar things could happen, I think, in neutron stars. Like stars could potentially destroy themselves by interacting with dark light. But I'm not too familiar with the literature there. Like the sun could shine dark light, for example, and that could cause some interesting things to happen to the sun and some other stars.
Yeah, that is fascinating. I guess one other question that I have is like, if we were to probe at higher and higher energies to the point where like we could, I don't know if I want to say like probing gravitationally, but like where gravity starts to become like more dominant and not as weak, would we then be able to see dark light? I don't know if see is the right word, but like at least observing interactions from dark light or dark matter in general.
I mean, I think of course if we have a larger accelerator, we're gonna be able to unlock, or study particles that have a larger mass. Because mass you can think of as kind of like a gatekeeper, because you have to overcome the mass in order to produce the particle. I mean that it may or may not help the case for the dark light. But what's interesting is when people talk about dark light, it's possible that this dark light is very heavy, right? If it's very heavy, then all these phenomenon, that it destroys black holes, that the sun can shine dark light, all these phenomena are irrelevant, right? Because when it's really massive, the only way for that particle to be relevant is if you have enough energy to produce them. And most things in our universe don't have that much concentrated energy right now, right? So when people talk about dark photon, they're usually referring to the possibility that these dark light has a very low mass or it could be totally massless. So they're somewhat similar to ordinary light, and to that extent, and this is one of the interesting aspects of particle physics. On that level, having more energy actually doesn't help you very much to study the phenomenon of dark light. Is actually about more clever experiments, more interesting astrophysical studies. And that's why, this subfield of dark light physics kind of pick up momentum. Because look, we don't have infinite money to dump into the next generation collider, even though many physicists would love to, for humanities to try that, personally me included. But we don't have that. But then the other frontier would be to try more clever experiments, more intriguing studies of cosmological objects like black holes, to see if there are maybe something that we've missed, like dark light, that are just hiding in plain sight.
Yeah, that makes sense. Especially if they're not at higher energy, then going to high energy wouldn't really help. Yeah. There's another audience question that I want to ask, which is how would entropy work in this dark universe?
Yeah, so entropy would work similarly. So like we mentioned before, um, for one thing, you can talk about the heat death of the universe. In this scenario, everything decays. We end up with a bath of ordinary light, right? And in this scenario, that ordinary light could be mixed with dark light as well. And dark light would contribute to the entropy of the universe. In fact, we know that we know how much entropy is in the universe near the Big Bang, right? And that's one of the reasons why there couldn't be too much dark light, because that would mess up the size of the universe, right? Roughly, right? But otherwise, yeah, if dark light exists, it could contribute to the way heat death occurs for the universe, and entropy will work just fine. There will be entropy also contained in dark light. It's the ultimate exhaust product, like light. Dark light will also be one of the exhaust product, and maybe with time, I don't think it can decay into light. I don't know what dark light will decay into if it's really light. That's something to think about. Maybe nothing actually. Yeah, so it will work just fine, but the dark light will also become a heat exhaust of the universe, possibly.
Huh. That would be interesting to see if we live that long. Yeah, so I realize we're almost at time. I want to give you a chance to leave the audience any parting words about dark light.
Yeah, I think it's a fascinating subject, and I think a lot of our episodes we talk about really deep theoretical problems in particle physics. but also understand that the field of particle physics is changing because there's so many theoretical problems that just seem so intractable, so impossible to solve, and sort of this new a lot of they're kind of like a somewhat of a paradigm change. A lot of these new development has been just asking the question of what if, you know, doesn't need any particular motivation, right? Because look, we have electrons and protons and neutrons and quarks and even neutrinos and different types of quarks. Like we don't really know why, right? We have no clue. There's no reason really for all these particles. When in the real world we're only made up of electrons, protons, and neutrons, right? Like what's up with the muon particle? What's up with the tau lepton? Like many of these mysteries we really don't have a clue. So it's who's to say the rest of the universe, things that we have not seen, maybe have no reason to exist whatsoever. Maybe and that's why dark light, it's a very sensible thing to consider. Well, it doesn't exactly solve any particular theoretical problem, at least not initially, but you got to start somewhere. Once physicists can start considering the possibility of dark light, there's so many, new understanding on what it can do, and maybe after a while people realize that it can solve some of the long-standing theoretical problems. So hopefully, I hope that this showcases that like particle physics isn't, some people like to say that particle physics is dead, but it's not dead. People are still coming up with novel ideas. Maybe the paradigm is a little different now, but physicists are still trying hard, being creative. Like physicists aren't so stuck minded that they're all stuck in the same old ideas. There are creative solutions, what ifs, and this is really the interesting crux of particle physics. I think as a young researcher, this is one of the reasons why people go into the field, because I mean, come on, it's interesting, right? Who can say that they spend the time studying whether dark forces can destroy black holes? I mean, like that's just sci-fi, but could be in real life. So
Mhm. Yeah, yeah, it is very interesting. So, well, on that note, I want to thank everybody for joining us. We'll see you all next week.
yeah, thanks.